Good evening, all of you. This is in continuation with the previous lecture. So, in the previous lecture, we have discussed about the internal field, the sum of the external field E and the field due to all the dipoles surrounding that point E dash. This net field is called as the internal field or the local field EI, and it is given by EI is equal to E, that is the applied electric field, plus P divided by 3 epsilon naught. This is for the three-dimensional solids. In this lecture, we shall discuss regarding the derivation of Clausius-Mosotti relation. Now we shall consider a elemental solid dielectric material. Elemental solid means the solids which are just atoms. Since they do not possess permanent dipoles, for such materials the electronic polarization exists. The ionic polarization, orientational polarization will be 0. Hence the polarization for these materials is given by P is equal to N alpha E into EL. EL is the Lorentz field or the internal field. So now we shall substitute for the Lorentz field or the internal field. N alpha E plus P divided by 3 epsilon naught. So now we shall solve for P in this expression. So I will take out P common here. P minus N alpha E divided by 3 epsilon naught is equal to N alpha E into E. We shall solve for P. P is equal to N alpha E into the field divided by 1 minus N alpha E divided by 3 epsilon naught. I will call this as equation 1. So where N is the number of dipoles that are present per unit volume, alpha E is the electronic polarizability, and epsilon naught is the permittivity of free space. E is the strength of the applied electric field. Also, we know that the polarization related to applied electric field is given by P is equal to epsilon naught into epsilon r minus 1 into E. I call this as equation 2. Both equations 1 and 2 represents the polarization. So I can equate equations 1 and 2. So we shall equate equations 1 and 2, and this E and this E get cancels, and we shall rearrange the terms. So we'll keep N alpha E, and we shall take LCM on the other side. This will be equal to, we'll cross multiply this to this side, epsilon naught into epsilon r minus 1 into E will retain, and we'll keep N alpha E divided by 3 epsilon naught to this side. N alpha E into E divided by epsilon naught into epsilon r minus 1 into E plus, I'll take out the other side term, N alpha E divided by 3 epsilon naught here. I will left out with 1 on the right hand side. So in these two terms I can take out N alpha E common. So I can N alpha E divided by 3 epsilon naught, I can take out common 3 epsilon naught. So I am left out with 3. I don't have 3 here, so I have 3 in the numerator, divided by epsilon r minus 1 plus 1 in from this term, and this is equal to 1. So I can write N alpha E divided by 3 epsilon naught is equal to, so I'll take out the LCM. So I will be left out as epsilon r minus 1 divided by epsilon r plus 2. So we'll take the LCM over here. Epsilon r minus 1 is the LCM. So I am left out with 3 plus epsilon r minus 1 divided by epsilon r minus 1. So it will be 3 plus epsilon r minus 1 will be epsilon r plus 2. So that will come into denominator. Epsilon r minus 1 will go to numerator, and this equation is called as the Clausius-Mosotti relations. So using the above relation, if the value of the dielectric constant of the material is known, then the electronic polarizability can be determined. So if the value of dielectric constant of the material is known, epsilon r, so you can calculate the electronic polarizability. So this you will get it in the problems.